Okay, yeah, thanks a lot, Netta. And yeah, thanks organizers for such a wonderful meeting and the opportunity to speak. So we'll be talking about some work which I did recently with my student Xuer Wadham, and which appeared sometime in August. So let's just consider, say, let's imagine you have a room with a gas of molecules. Let's imagine the system, say the initial state is a highly non-equilibrium one. Say you arrange all the molecules in the very special configuration, but each molecule has very large, say, kinetic energy. Okay, and now you let the system evolve, and then all those molecules will collide with each other, and they will quickly thermalize, and then you will reach an equilibrium state. Okay, so after the system reaching the equilibrium state, then say the microscopic properties, they essentially remain the same, no longer change with time. But the system still remains to be a pure state because of the unitarity of quantum mechanics. So we call such a state, say, an equilibrated pure state. So from all purpose, say, for many purpose, this kind of equilibrated pure state just behaves like a thermal state. Okay, we can use thermodynamic quantities to describe microscopic properties of the state, and those thermodynamic quantities will obey the laws of thermodynamics. And also, if you make, say, measurements on any small fraction of the system, and such measurement can be well approximated by those in the, say, some kind of equilibrium density operator. So here I just write down the canonical ensemble, say the system, say from our daily experience, the gas in the room, they behaves like a thermal system, even though it might be a pure state. Okay. But if we use quantum informational properties of rho e to approximate those of psi, and then we immediately see there's a violation of unitarity, because say, let's imagine we consider, say, Rayleigh and the von Neumann entropies, say, for some subsystem A and its complement A bar. And then, so from unitarity, if you are in the pure state, then SA should equal to SA bar. So N here is the Rayleigh index. So you should interpret N equal to 1, say, as the von Neumann entropy. Okay. But if you are in the density operator, and then this equality is not satisfied. Okay. Not even approximately. Okay. And this is actually precisely the situation we face in the evaporation of a black hole. So if you think about a black hole, imagine you say the black hole is formed from collapse of a star in the pure state, and then the star collapse, and then form a black hole, then the black hole starts evaporating. So let us assume that the evaporation process is very slow, as is typically the case for a very big black hole. And then you can imagine each stage, say, at any given time for evaporating black hole, you are in some kind of quasi-static equilibrium. And then such a black hole then will be in the equilibrated pure states. Okay. And again, if you use the Rayleigh or von Neumann entropies of the, and the black hole for all purpose, for many purposes, behaves like a thermal state. And say if you make has a finite temperature, and if you make any local measurement, and then behaves just like a thermal state. But if you use the Rayleigh and von Neumann entropies of the, say, corresponding thermal state to describe the evolution of a black hole, then again you violate unitarity. So this is the one version of the Hawkins information paradox. Say, if you calculate the entanglement entropy, say, associated with such a density operator, then you find the entropy keep increasing. But of course, the unitarity implies that the evolution of the entanglement entropy for the system should obey this page curve. Say after increase to a certain point, then you should go down. Okay. So a key question here is what level of knowledge, say, of your pure state is actually needed to obtain, say, Renyi or entanglement entropy that is compatible with unitarity.
Hong, we have a quick question, it looks like.
Yeah, okay.
Raphael, please go ahead and mute yourselves.
Yeah, Hong, can you just clarify why you say that this is a paradox, since it's not a paradox for the condensed matter systems or other systems that you gave examples for?
Oh, yeah. No, this is not a paradox. If you assume the black hole is unitary, evolution is unitary, and then of course this is this is not a paradox. If you believe that the evaporation of black hole is unitary, then of course should satisfy the page curve, and then there's no this is just one version. Then there's no paradox. Yeah, do I answer your question? Okay, good.
Yeah, sorry, I was muted again, so it took a while.
Okay.
It doesn't stay somehow. I don't know why. But not really. I mean, I don't understand why you even say that it's a version of the paradox. I just don't think it has anything whatsoever to do with the paradox. But maybe I should let you go on.
Yeah. Say, why do you want to calculate the page curve? Yeah,
because I think that black hole evaporation is unitary. So we should be able to obtain that curve.
Yeah, we should obtain that curve. But if you do a naive calculation, then you don't obtain that curve, right? Yeah, that's one version of the paradox.
Well, I would say obtaining that curve establishes unitarity. The paradox arises because it's hard to make that compatible with a smooth horizon, which doesn't appear in this analogy.
Sure. But that's why I call this is one version of the paradox. So one version of the paradox, if you do a naive calculation, you don't see the page curve.
I just don't think that there is any version of the paradox that does not include a discussion of the horizon, of the smoothness of the horizon. You can only have a contradiction between two things if you introduce them both. But
sure. That aspect, I perfectly agree. I'm just saying when Page introduced his page curve, and he didn't use anything about the black hole horizon. Okay, just treat the black hole as a quantum mechanical system, then that should satisfy the page curve. But if you do a naive calculation, you don't see it satisfy the page curve. I'm just referring this aspect of the Hawkins calculation. Yeah, if you don't call it the paradox, certainly I agree with you that the real paradox is at the horizon. Yeah. Anyway, let me just continue. So, so the key question is actually what level of knowledge, say of psi, is actually needed to obtain this entanglement entropy or Renyi entropies that's compatible with unitarity. Okay, and in other words, what inputs are needed actually for us to derive the page curve? Okay. So the question is the knowledge of this approximate density operator enough to actually obtain a unitarity answer compatible with the unitarity, or actually you need more refined knowledge, say, of the initial state. Okay. So the recent surprise from the derivation of the page curve from gravity, okay, which is a strong support for the unitarity of the black hole evolution, actually used only the knowledge of rho e, okay, and you actually don't use any, you don't need to use any refined information, say, of your of an initial state. So what you need is essentially the black hole geometry, and which is essentially the cross-grained quantity encoded in rho e. And so this has often been referred to say, as the magic or miracle, say, of Euclidean gravity path integrals. So somehow Euclidean gravity seems to know somehow this kind of fine-grained information. Okay. So the message I want to convey in this talk are the following. So first, I will introduce a general approximation scheme to calculate this Rayleigh or entanglement entropy for such a equilibrated pure state that is compatible with unitarity. But actually, the answer only depends on the equilibrium properties alone. Okay, does not only depend on your information about the rho E. Does not depend on any other details of your initial states. Okay. And such a scheme applies to general quantum many-body systems. Okay, and that equilibrates, including the gravity system. Okay, as well as gravity system. And in the gravity system, then this can be address this version of the paradox, which is how you. Yeah, maybe I should. Yeah, just Raphael's objection. Maybe it's better how you understand to obtain the page curve. Okay. And in the limit of large number of degrees freedom. And so from this perspective, what is usually called the magic, say, of computing the page curve from semi-classical gravity is actually more of the magic in the observables, such as entanglement entropy or Rayleigh entropies, rather than the magic of Euclidean gravity path integrals. So essentially, this property actually applies to all many-body systems in the limit of large degrees freedom, not just gravity. Okay, so you can actually with just semi-classical information, it is enough to obtain an answer which are compatible with the page curve. And then and this approximation scheme generalized the page result to finite temperature and also infinite dimensional Hilbert space. So so recall that the page result was based on, say, average of the pure states for finite dimensional Hilbert space, and which actually corresponding to, say, infinite temperature, because you can access, you assume you can access every state in your Hilbert space. Okay, there's no energy constraints. So and this approximation scheme can also also because the page result was being obtained by average over the pure states. It's not something you can actually systematically improve. And so this approximation scheme can actually in principle be systematically improved to get more refined information about your system. And the third aspect is that this approximation scheme provides actually a precise prescription for deriving replica wormholes, and explains why they give a result compatible with unitarity. Okay. Yeah, again, this just explains that there's no magic, say, in the fact that somehow replica wormholes give you a result compatible with the page curve. And also, this shows that the replica wormholes can rise in the theory with a fixed Hamiltonian, and the low ensemble average is needed. So let me just pause here. Do people have some questions regarding so far? Okay, good. So yeah, so let me just reiterate the setup of the problem. So again, we can see that you start with the initial pure state, and then imagine evolve the system for some time, then the system has equilibrated. Okay, so we call this equilibrated pure state. And then we assume that macroscopically, this, say, equilibrated pure state can be approximated. Certain properties can be approximated by some equilibrium density operator. So I write it in this form, and this I alpha is an unnormalized density operator. and the Z alpha is just its trace. Okay, and so I call the Z alpha the effective dimension of the operator. Yeah, which characterize, say, the number of effective degree of freedom. Say, and this alpha just say equivalent parameters such as temperature or chemical potential. And so the finite dimension, say if you have a finite dimensional Hilbert space at infinite temperature, if there's no energy constraint, and then this I then just corresponding to the identity, and the Z just corresponding to your dimension of your Hilbert space. And you can also consider, say, when you have energy constraint, you can consider macrocanonical ensemble, or you can consider canonical ensemble. And then you may consider other more general, say, ensembles, say, generalized, say, with chemical potential, yeah. Good, so so this notation alpha, I will use it often. Yeah, so keep in mind this notation like alpha. So now the Rayleigh entropies of the system then can be just, yeah, let me introduce this Z, which is exponential of the Rayleigh entropy. So I call it the Rayleigh partition function. And then you can just write it, yeah, as the trace, you first trace over the complement of the system. So U is your evolution operator, and the rho 0 is your initial density operator. You trace over the A bar, and then you take power n, you trace over A. And now you can write this in the path integral form. Say each U, then in the path integral give you a path integral of A from 0 to T. And then this nth Rayleigh entropy then give you, say, a path integral with 2n copies. Yeah, 2n copies of the path integral. So you have NU, which going forward in time, and also NU dagger, then which can be drawn going backward in time. And then the integrand of the path integral, yeah, the initial state of the path integral is controlled by your rho 0, and the final state is controlled by this kind of trace. Yeah, the final configuration is controlled by the trace, which you use to calculate the Rayleigh entropy. And the integrand is the action, say exponential of the action associated with each contour. So there are n of them moving forward, and the n of them moving backward. Okay. And yeah, so keep in mind that this Rayleigh partition function, yeah. Again, this notation I will use over and over. So now, so in our discussion below, the permutation group will play a very important role. So yeah, so let me give you an intuition, a heuristic intuition where the permutation group come from. So now let's look at this path integral for this Rayleigh partition function. And now there's then there's actually a special subset of configurations. Because you had, because of this structure, you have this sum S phi I minus S phi I prime. Okay. So if the set of phi I configuration which going forward in time, and the set of phi I prime which going backwards in time, they're just related by some permutations. Okay. And then
Hong, we have a raised hand from John Source.
Okay.
Hi, Hong. Could you just take a second to explain this image in the top left a little more thoroughly? In this Rayleigh partition function you've described, you have a U and then a row and then a U dagger and then a U and then a row and then a U, or you have, you know, some you have many U's sandwiched with many rows, I guess. Yeah. I'm having trouble parsing this figure where there's one line that's row naught at the bottom and then a bunch of U's connecting that to a trace.
Yeah, yeah. Yeah, I can make that a little bit. Yeah, this just follows if you just yeah, I will make that a little bit more precise a little bit later. Yeah, just wait a little bit. Yeah, this is just a heuristic way for you to show that you can write. Yeah, because you have two NUs, you can write them as the as n copies of the path integral. Yeah, as n copies of the path integral. And then heuristically, you can imagine that the rho 0 provides the initial state for these n path integrals. And yeah, there are n copies of them. Yeah, we'll make that precise a little bit later. And then you can imagine that this trace then provides the how you conclude this path integral. Yeah, the only thing to show here is that you have NU and NU dagger, and then you can always write in this form.
Yeah, thanks so much. That helps a lot.
Yeah. Okay, good. So yeah, so there are special set of configurations which are just related by permutations. And because they are related by permutation, this minus sign, so the whole for this subset of configuration, so the whole integram just vanishes. Okay. So now if you consider say many body systems say evolve for a long time, so you may think that actually this exponential can be fluctuating a lot. And then for most of the configuration, they will average to 0. So except the configurations which satisfy this kind of special set of conditions. Okay, which the exponent is identically 0. Okay, so intuitively they could dominate the path integral. Okay, and in particular, when such kind of configuration dominates, the result is actually time independent because the integrand because the integrand just become identically 1. And then, yeah, there's no time dependence. Okay. And so this suggests the relevance of the permutation group. Yeah, so this is a heuristic way to suggest the relevance of permutation group. Okay, so now I will be more precise to describe the how we do the approximation. Good. So again, this is the heuristic way to write this path integral, and then you can view this as a transition amplitude in the 2n copies of your Hilbert space. Okay, and with the unitary evolution operator given by U times U dagger. And so you can actually mathematically write a precise form as a transition amplitude in these 2n copies of the Hilbert space, by defining an initial state in these 2n copies of the initial 2n copies of Hilbert space using the 0, and then yeah, and then the trace defines the final states. Okay. Okay, so now let me just quickly tell you how we define those states. So first, just a general remark. So for any operator, so acting on original Hilbert space, okay, you can always define a set of n factorial states as follows. Okay, so for each in the 2n copies of your Hilbert space, you can define a set of these n factorial states, and each one of them is associated with an element of the permutation group. So these states are labeled by O, original operator, and the element of the permutation group, and this is the element of the 2n copies of a Hilbert space. So we define this kind of state by looking at its, say, overlap with a basis of these 2n copies of a Hilbert space. Say let's just take some some basis of this, say I1 corresponding to the labeled basis for one copy, and then you have I1 prime for the second copy, and then you have n of them. Okay, so this is just a basis. And then we define the overlap of this state with the basis in terms of the matrix element of the O. Okay, so in terms of matrix element of O, and the permutation group plays the role which you permute the second indices of the matrix element. Okay, yeah, since you may not have seen this say on daily basis, so let me just leave this for a second for you to stare at it. Anyway, just the point is that for any operator, you can always associate a set of these n factorial states defined this way. Okay. And for the identity operator, we just suppress this O, we just call it sigma, and then just corresponding to, say, a product of chronic deltas with various permutations. Okay. Good. And then there are two special permutations. One is just the identity, and then the other special permutation, which we will use a lot later, is what we call eta. This corresponding to using the cyclic notation means that the nth element go to n-1, and n-1 go to n-2, etc. Okay. And and the use of this kind of notation is that they can capture the trace structure in a very compact way. Say, for example, if you take O associate the state for O associated with the identity a permutation, and then contract with the identity operator for the identity permutation for the identity operator, and then you just get the trace O to the power n. And if you take to overlap with this eta, and then you get trace O to the power. Okay. And then and then this way, then you can show that this original the explicit form of that kind of Rayleigh partition function then can be written as a transition amplitude of this form in the 2n copies of your Hilbert space. Okay, and so rho 0z defines your initial state, and the E is the identity permutation, and eta is this, and then your final state, which controlled by this trace structure, trace A bar and trace A, and then can be captured by the permutations associated with the identity operator. Okay, yeah, anyway, this is just a very compact way to capture the algebraic structure of your Rayleigh partition function. So now we can, using this structure, we can state our approximation. So for this purpose, let's just consider the sets of n factorial states associated with this unnormalized equilibrium density operator. Okay, recall that this I alpha is the unnormalized equilibrium density operator we use to approximate your pure state. And and now let's imagine consider the projector into the subspace of this n factorial states. Okay, so those states are not orthogonal to each other, so there's a non-trivial metric in this subspace. Anyway, so this is the projector to this subspace, and so one important property of this subspace is that it's invariant under the evolution. Okay, and this can be easily understood because this is by definition the equilibrium. Unnormalized equilibrium density operator, and then they should not evolve under the time evolution. And now we can split the identity into the projection into the subspace and the complement. Okay, we just call Q. And now let's look at this expression for the Rayleigh partition function. And now you can just insert. Okay, now you can just insert this identity in these two places. Okay, and because this U leave this I invariant, of course, it also leaves P invariant. And then so act on for U act on P, essentially you can just forget about U. Okay. Anyway, so and then that leads to two pieces, and the one just corresponding to projector into the subspace corresponding to P, and then there's a complement part. And now the approximation, and there's no cross terms, due to this property. Okay. And now the key is the key idea of approximation is that in the limit of the large number degrees freedom, we just ignore the second term. Okay, so the claim is that in the limit of large number degrees freedom, the leading expression for your Rayleigh partition function just given by the first term. Okay, and you can just forget about the second term. And now you can also further show that when the system is large, and for pure initial state, you can actually further write this Rayleigh partition in the following form, and then just become the overlap between this kind of the set of states associated with your equilibrium density operator with this final state which captures the trace structure. Okay, and so this applies in the regime which this partition function is much greater than 1. Okay. So in this form, we see that this Rayleigh partition function and also the Rayleigh entropy then it's solely expressed in terms of the equilibrium density operator. And now the details of initial states are completely forgotten. Okay. So the highly non-trivial thing is the sum of the permutations. Okay, you have the sum of all permutations. So now if you take the naive equilibrium approximation, say take tau equal to identity, then that's just corresponding to you approximate the Rayleigh partition function using the Rayleigh entropies of the thermal density operator, of the equilibrium density operator. But now this approximation goes beyond that. Okay, include all those non-trivial permutations. And this approximation can also be, you can also apply a similar kind of approximation to other observables in the pure state, say correlation functions. Yeah, not just the Rayleigh entropies. So anything involve equilibrated pure state, say require some kind of replica, and then you can apply this kind of approximation. Anyway, so now let me just state the general features of this result, okay? And then, so let me just write each term here by dependence on this permutation element by this tau and then ZA tau. So one key thing is that you can check that because you sum over all permutations, and this actually satisfies the unitarity constraint. Okay, even though it just expressed by equilibrium density operator, but actually manifestly satisfy the unitarity constraint. So there are actually two particularly simple contributions among this sum. So one, as I mentioned, is just corresponding to the identity permutation. So for the identity permutation, and then you find, and this is just given by the Rayleigh partition function of your equilibrium density operator. And another special configuration is what I mentioned, this eta, corresponding to the cyclical permutation. And then for this permutation, and then you find that you just get the Rayleigh partition function of the A bar. Okay, equilibrium partition function, equilibrium Rayleigh partition function of A bar. Okay. And so this is the Rayleigh entropy of the then can be expressed in terms of the Rayleigh entropies of equilibrium any Rayleigh entropies of the A bar. And then, but other permutations will involve more complicated trace structure, and then you cannot express them. Yeah, a more complicated trace structure involving between A and A bar, you cannot write them in such a more intuitive form. And then now you can show that if one of A or A bar is much smaller than the other, okay, and then you get this result, and then you find either one of them will dominate, okay, then the other will all become small, and one of them will dominate, and then you get this answer. And then you just get the minimum between the equilibrium entropy of A and the equilibrium entropy for the A bar. And again,
we have a question.
Okay.
Alex, go ahead.
Yeah, quick question, Hong. The other permutations, the more complicated ones that you're not talking about here, are they related to replica symmetry breaking?
No, they are. So yeah, we have no here. We're not doing any side point, etc. Here, it's just you still have still you have n copies and each copy are the same. Yeah, you just contract the different copies in different way.
So in every individual term, replica symmetry is preserved in some sense, or does replica symmetry, is it preserved by doing the sum over all permutations?
Let me think. So I think each individual term, now I see what you mean. I think each individual term may not preserve this replica symmetry. Yeah.
Thanks.
Okay, good. And So now, so this is the generalization of the page result to finite temperature. And if so there was a famous page result before when the A or A bar is much smaller than the other. If you have a finite dimensional Hilbert space, say at infinite temperature, and then this is a generalization of the page result to finite temperature or infinite dimensional Hilbert space. So this is very intuitive, but okay. So now let me mention another general feature. So now suppose you you have the this. Suppose your equilibrium density operator can be represented by some Euclidean path integral. Okay, as often the case, for example, for the canonical ensemble. And then the whole thing can be just written in terms of Euclidean path integrals. And for n replicas of I. So now in this remember the original linear partition function involving the 2n copies of the Laurentine path integral. But now in this approximation become n copies, n replicas of the Euclidean path integral. And so again, so for the rho E, for the tau equal to identity, and then just corresponding to the standard, say, contraction between n replicas corresponding to your standard linear entropy for A, okay? And then if you take tau equal to eta, then corresponding to the standard contractions, you get the linear entropy for the A bar. But you can also have more exotic permutations. For example, here the 3 copies, you can have this tau, and then involving more exotic contractions between A and A bar. Okay.
Honk 5-minute warning.
Oh, okay. Good. So so now you can check the validity of the approximation. So so let's consider, for example, consider the part we throw away, this ZQ, and let's look at the square, and then apply equivalent approximation to this to the part you throw away. Okay. And anyway, so so this provides a self-consistency check that if the part you throw away, you use equivalent approximation to the part you throw away should be much smaller than the part you keep. Okay, and this criterion is also the same as that your equivalent approximation should commute with the factorization. Anyway, so so you find that this approximation is self-consistent when the number of degrees freedom is sufficiently large. So remember, Z1 is the partition function, and so this is suppressed. So the correction is suppressed by the 1 over the square root of your partition function. Okay, and so it's also possible to derive, say, this equivalent approximation by making some minimal assumptions, say, on the spectral properties of the Hamiltonian and the initial state, etc. And again, you can show that this actually dominates in the large number of degrees freedom limit. So now let me make some remarks on the gravity system. So this equivalent approximation can be applied to gravity systems, so also in the equivalent pure state, such as a black hole. And then now this just involving some kind of gravity amplitude. Okay. So if gravity respects, say, the usual rules of quantum mechanics, and then this prescription then leads to answers consistent with unitarity. And then you can just use this prescription to derive the page curve, say, without any suspense. Just guarantee the page curve should come out. If you have applied this rule consistently. Okay. And so, so this is, as I mentioned earlier, this is one version of address the Hawkins paradox that the black hole evolution should be unitary. And this may be, so this kind of amplitude can also be implemented at the semi-classical level using the Euclidean path integrals. Say if you can represent this I alpha for your gravity system, such as a black hole, using Euclidean path integrals, and then you can just calculate it. Okay. And then for holographic systems, say, for example, the boundary version of the prescription then provided the boundary conditions for formulating the prescription for the Barker gravity. So intuitively, the coupling among different replicas should net to replica wormholes, and then the geometry is connecting different replica universes. So emphasize this is still approximation, even if you can calculate this amplitude exactly in gravity, because in reducing the question in terms of the Euclidean path integral, you have already done approximation. Okay. Even if you can do the Euclidean path integral exactly, even if the Euclidean path integral can be used to define your quantum gravity exactly, this is still approximation. Okay, so now let me just quickly tell you, say what happens if you apply this to this simple black hole model considered by this Stanford group. And then the idea is straightforward. You just write down your equivalent density operator, okay, to approximate these black hole states, okay, and so there the radiation is just treated as infinite temperature. So you can ignore, there's no constraint on the radiation part, and the black hole is put at the finite temperature. Okay. Then the black hole is some kind of thermal density operator. Yeah. Anyway, so now you can just say, you can just directly write down the answer. Okay. Or you can just, yeah, you can just use that equivalent approximation to write down the answer, and the answer is guaranteed to be compatible with unitarity. And the key is that this final answer is all expressed in terms of the partition function of some powers of this I beta of the equivalent density operator. Okay, and yeah, just involving the partition function of your equivalent density operator raised to some power. There's nothing. There's no other information is needed. And so now you can apply explicitly to their discussion. And then when you have the end of the world brane, so in addition to have this thermal part, you also have the part contribution for the end of the world brane. And the details of this part is not important. And anyway, so this is the so this equivalent approximation prescription give you the boundary prescription how you should calculate this kind of partition function, and then you just use the standard rule of ADS-CFT, and then that just translates into this kind of replica wormhole kind of geometry discussed by those authors. So they really have one-to-one correspondence. Yeah, it's just essentially you can just using standard ADS-CFT prescription. Now you can just derive the replica wormhole configurations. Okay, so this actually provides the precise prescription when and how you introduce replica wormholes. Okay, and also explains the why somehow just by Euclidean semi-classical Euclidean gravity you can actually calculate the entanglement entropy of a pure states which are compatible with unitarity. Okay, and then the procedure guarantees that the answer will be always satisfy the page curve. And the underlying mathematical structure, say just the permutation, okay? And actually, I will not have time to explain for those planar configurations corresponding to the non-crossing permutations they dominate. Anyway, so also physically, this shows that the replica wormhole can actually arise in systems with a fixed Hamiltonian, okay? So this derivation, so this approximation is derived for a system with a fixed Hamiltonian. So in this Stanford group paper, so they described some reason for why maybe this replica wormhole could correspond to ensemble average, because there's some tension between you use this wormhole approximation to calculate, say, the second linear entropy, and then when you use this approximation to calculate the matrix element. And somehow one does not lead to the other. Okay, it looks like some kind of factorization properties are violated. But this incompatibility can be easily understood using this equivalent approximation, okay, which we discuss in detail actually in our paper. So the point is that at the leading order in equivalent approximation, the off-diagonal term of your density the off-diagonal matrix element of your density operator is actually a subleading. But those subleading terms actually contribute to your calculation of the linear entropy. Okay, And so this is just say if you include those higher order contributions from the approximation, and then there's no tension at all. You don't need to introduce any ensemble average. You can also apply.
So we're going to go time. So if you can try to wrap up quickly.
Okay. I'm wrapping up. Yeah. So you can also apply this to say internal black hole coupled to a bus, and again, you can also apply it to other systems. For example, a big black hole in ADS, say form collapse over pure states, and then this again instruct you how to get the answer which is compatible with unitarity. Okay, this approximation provides powerful tools for studying quantum information properties of the quantum systems, so both condensed matter and the gravity systems. So here I've just mentioned some quick gravity, say potential gravity applications, for example, finite temperature effect on the page time, and correlations, different quantum correlations among different parts of the radiation, information transfer from black hole to radiation, and etc. And also, let me just conclude. So here we introduce this equivalent approximation, which we throw away this term. So the term we throw away has an intrinsic description in terms of Lorentzian path integral in 2n copies of the original system. So if you want to see this, the effect of this term, say in your gravity path integrals, you actually have to go to the intrinsic Lorentzian path integrals. Okay. And also, but you can try to study, say, the physical effect of such kind of term, say, in some model systems, say, some model condensed matter systems. And also, finally, let me just make one comment. So Euclidean wormholes say arise in many different contexts, say of semi-classical discussions. People have discussed them in many different contexts. So even though they all look alike on the gravity side, but depend on the context, they may be responsible for completely different physics. So they actually may have completely different boundary interpretations. So some of them may correspond to ensemble average, some of them may not, etc. Okay. And for example, the replica wormholes for the page curve are relevant for time scale which is much, much shorter than those kind of wormholes which you use to calculate the spectral form factors, say in the paper by Satz, Stanford and Schenker. And those just concern completely different time scales and completely different physics. And so could well happen, say one of them say appear in the system with a fixed Hamiltonian, but the other may require ensemble average. Okay, so our replica wormholes, so arising systems with a fixed Hamiltonian, they may not say anything regarding those wormholes in other physical contexts. I will stop here. Thank you.
All right, thank you, Hong. I'm just going to unmute everyone, or ask everyone to unmute so we can all clap and see if this succeeds. So I've asked everyone to unmute, so thank you. Go ahead and mute everyone. So, okay, so let me go ahead and we'll go ahead and take some questions. So, Xiaoling, please go ahead.
Hi, hi, Hong. So this sum over permutation you wrote down. That's equivalent to averaging over a pure random initial state. So if you take a random state in this in the space specified by this I alpha, and then you then there's a pure state, and then you average over the density operator n copies, then that's equivalent to the sum over. But it seems like your approximation is saying I'm assuming after that time evolution, whatever initial state is evolved to a random state in that subspace.
Yeah. I think you can. This is one possible interpretation, of it.
So that seems. I mean, that should be true in externalization, but is it a little too strong? Like in the black hole case, if a black hole after a long time is like such a state, but then I can send in a particle. There is a particle right behind the horizon. Then there won't be a random state like that, right? I'm just wondering whether that's a little too strong.
Yeah. So if you send the particle behind the horizon, that's corresponding to much higher order effect than we calculate here. And so this is really the leading order in the number of degrees freedom. Yeah, so if you send a single particle, yeah, of course we will not see that.
Okay, thanks.
John Source, go ahead.
Hi, Hung. So you commented that you find replica wormholes coming out of a fixed Hamiltonian without an ensemble average, and they came from this approximation prescription where you sum over all of the permutations of this equilibrium calculation. The lore that a lot of people use in the modern literature is that the reason we have wormholes in fixed Hamiltonians is because those fixed Hamiltonians are chaotic, so they have signatures of ensembles even if they aren't ensembles. I'm wondering if there's a connection between these two ideas that you can comment on that you've thought about, whether the, wormholes arising from effective ensembles from a chaotic single Hamiltonian is related to the sum over permutations for your single Hamiltonian. Yeah,
I think that there's no contradiction with this kind of this is related to the kind of idea, say observables, say like Rayleigh entropy or the von Neumann entropy, they may be self-average, and so for chaotic system or sufficiently non-integrable system, they behave they can behave very much similar to systems you just do some kind of average. Yeah. Does this answer your question?
Yeah, I think so. Thank you.
Okay. Yeah.
Karen Fernandez.
Hi, my question concerns this your slides on general features. I think it was general features 3.
Okay.
So you had those diagrams, and it looks like I understand the first two, which I think is when you have n copies of one system and n copies of the other system. That's the first two, right? A and B. And those come from the from considering the sum which is given in that approximate expression. But I don't seem to understand the third figure, this exotic case, so to speak. I mean, how does that follow from that approximate expression?
Oh, you just let me just you mean the third one, this one, right?
Yes.
Yeah. So this expression just essentially give you an algebraic way, tell you, say, when you have a system A and A bar, how you take the traces among different subsystems. And then the first two, then corresponding to the permutation of E and eta. Yeah, you just mechanical, you just plug in the definition of E and eta, then you find that this contraction, which is a standard one, say for the Rayleigh entropy of A and the Rayleigh entropy of A bar. But now if you plug in the tau corresponding to this permutation, and then you find the corresponding to this more exotic contractions.
What I mean to ask is, like on the previous slide of this, I mean, just on the previous slide of this.
Okay. You mean this? You mean?
No, I guess. Sorry.
Right.
This one, yeah. So those two cases of E and eta are basically what we have, right? These are the two approximations that we end up having from taking the sum. So the third one is it okay? I think I get. Okay, so the third one is in a case where A and A prime are not smaller, like one is not much smaller than the other. Is that?
That's right. That's right. Yeah. Okay. So when one of them is much smaller than the other, then one of E or eta dominates. But if they become comparable, and then there are many more permutations can dominate.
Okay. Thank you. Yeah.
Do we have any other questions? There is a question in the chat, Rafael, if you wanted to. Oh, sorry, never mind. We have a raised hand here. Juan, go ahead.
Yeah, so I thought that in the case of the black hole coupled to radiation, the entropy, for example, of the black hole system is not exactly equal to the entropy of the black hole in equilibrium. There is some difference because of exactly where the location of the quantum extremal surface is. Does your discussion take this into account or not?
Yeah, so I think it should. Yeah, so it depends on the details how you write down. So there's some freedom how you write down that equilibrium density operator. For example, if you have the end of the word brain, and then the end of word brain contribution will go into that. Yeah.
The way I understood this is that this works for the West Coast model, but it's not obvious to me that this works for black hole coupled to radiation.
So for the black hole coupled to radiation, the story is a little bit trickier. Yeah, indeed. So there you have to use some kind of local approximation because the radiation is infinite, and then you have to use some kind of local approximation for the radiation part, because now we discussed this aspect in the paper. Yeah, so there indeed some more subtlety in that case, just because the radiation is infinite. Yeah, there's some further approximation. Yeah, there's some further approximation you need to do. Yeah.
You mean this infinity has to do with the splitting of the radiation from the black hole, or?
Yeah, it's how. So you have to assume that the whole system equilibrates, and then when you have infinite radiation, the whole system cannot equilibrate. They can only locally equilibrate, and they can the assumption itself assumes that the whole system equilibrates, and so for the compact system you can certainly do that, but for uncompact system then you can only assume the local equilibration. And then that will introduce a larger nature of subtlety. Yeah. Yeah. So so I don't know precisely whether that will recover that small differences. That's certainly a very good question to think about. Yeah.
All right, so we need to transfer talks. So Hong, if you could stop sharing.
Okay.
Sorry, let's first thank Hong one more time. So